All right. So our next lesson we're looking at is going to be torque at 90 degrees, specifically when objects are in equilibrium. All right. So a couple things. One, a body in translational equilibrium will have no acceleration in the x or y directions, right? So it's going to be constant. However, while it may not have no acceleration, it could still be rotating. All right. So think about if you have one of those spinny chairs, right? Chair that can rotate. Right. If you're kind of providing some constant force, so you're moving, rotating at a constant rate, right? All the forces are going to be balanced. It's going to have a net force of 0. However, you can still be in rotation, right? This is going to be kind of that form of dynamic equilibrium. All right. Now, a couple things. Again, we're talking about torque right now. So this is essentially the rotational version of force. So, right, just start by defining it through a little example. So it's consider a seesaw or a teeter-totter, where you have a 100-gram student on one end and a 50-gram student on the other, or kilogram rather. All right, we're looking at the net forces in this case, right? In the x direction, we're going to have a net force in the x direction of 0, and in the y direction, also 0. All right, so let's draw this out. All right. So, although the net translational forces are 0, the system does still have a net torque. All right. So this seesaw is not going to be in equilibrium. All right. So we know that an object in equilibrium must have both translational and rotational equilibrium. Because again, in this case, you know, right, that for this particular object, it's going to be moving. Right? Put a heavy kid on one side and a lighter kid on the other, right? The whole seesaw is going to rotate, with the heavy kid pulling it down and the light kid being pushed upwards. Right? You are applying a force that will cause rotational motion. Right? And this is torque. So, if you want to remove any rotation and have no rotation, you must have no net torque. So let's talk a little bit about what torque is. We kind of introduced it yesterday, or our Monday lesson. But when we're talking about torque, we use the Greek letter tau. Right? It's lowercase tau. And this is going to be equal to a linear force times distance. Or you'll often see it as F times R, right? R is used on your equation sheet for distance when we're talking about torque. And then if we have an angle, you can also define it as FR sine theta. And our unit for torque is going to be Newton meters. A couple things. Torque is a vector quantity, right? Magnitude and direction, just like force. All right. So when we talk about an object being in rotational equilibrium, that essentially means that our net torque will equal 0. Another way we could say this, right? We're talking about rotational motion. We're talking about rotational motion. There's two different directions, right? An object can be moving clockwise or counterclockwise. So if it is in rotational equilibrium, then that would mean that our clockwise torque is going to be equal to our counterclockwise torque. So you see C or CC, that references clockwise or counterclockwise. So we're going through a few of these problems. You'll see me using tau equals FR, remembering that R is just going to be your distance, specifically distance from your force to the pivot. So let's take this example problem. Again, you can pause to work it out on your own first. But let's say you are doing a real life problem where you're trying to remove the bolts from your car, the lug nuts from your tire, so you can change out your tire. You know that the longer wrench you use, the easier it's going to be. Okay? So we have a torque of 24 Newton meters is going to be needed to tighten your nut. If a person can apply a force of 100 newtons, what's going to be the minimum length of your wrench that's required? Yeah, we have a relatively simple formula that we can just plug this into. In this case, we're focused on solving for R, right? Distance to the pivot, which is going to be our torque divided by our force. We know our torque that we're going to need is 24 over 100 newtons. I see newtons cancel out, so we're left with 0.24 meters. Is going to be the minimum length for our wrench. Obviously, the longer it is, the easier time we're going to have. Okay, a couple terms we want to go over before we move on. We're talking about center of gravity, right? This is going to be a very common concept, right? It's where the average mass acts. It's a different color. So this is also where we draw FG. Okay, uniform beam. Specifically in AP Physics, in real life, when we're talking about torque and we're talking about beams that we're applying a force to, it can get a little complicated, right? Because beams are made out of all different materials, different densities. They're not always consistent, so it's important to know when you see the term uniform beam, which you can assume most of these questions are going to include, even if it's not stated. But uniform beams have constant shape and density. Okay, and finally, arbitrary position of rotation. Right, if we have an object that we know we're going to rotate, right, if we're not given a pivot point, that means that you get to choose the location of your pivot. All right, so just a couple terms to kind of look out for. So you choose location and pivot. Okay, so a few little example problems here. So we have a 350 Newton sign hanging from a pole, again, that we can ignore the mass from. The pole is attached to a wall by a hinge and supported by a vertical rope. What is the tension in the rope? Okay, so again, we see that this is 350, so we know the tension in our rope, right? All right, which is the y direction. This should theoretically, right, make up for that 350 newtons that is being pulled down. Now we know that this is all in equilibrium, so our sign is not moving, right? It's not falling. it's obviously not lifting up. So a couple things we can look here, right? We know that this is in rotational equilibrium. So we know that our clockwise and counterclockwise torques are equal, which means, right, the sine is trying to pull it down and move the pole clockwise, and then the rope is trying to pull up and move it counterclockwise. So these two rotational motions are equal. And we can define them, right? We know that torque of the sine is going to be force times distance to the pivot. So the force is due to gravity, and then we have distance to the pivot, which is going to be equal to tension of our rope times distance to the pivot. Now again, we're trying to solve for tension in the rope. So we get all of this divided by R2. All right, we know that the force of the sine, right, gravity is pulling down with a force or a weight of 350 newtons. The distance to the hinge we're given is 1.3. And the distance of the rope from the pivot is 2. And so we're calculate all this out, and we'll get about, rounding up a little bit, 228 newtons. All right, so that's the tension in our rope. It's 228 newtons. All right, looks good. But wait, you might say, 228 newtons does not equal 350. Obviously, the pole itself, right, it's just in the x direction, right? So there's no y component there. So what's happening to that remaining force, right? How is this sine not accelerating downwards? Because given the information that we have, you would think that it would be. This gets us to this next piece here. All right, where it's asking, what's the vertical and horizontal components of the supporting force provided by the hinge in the last question? So let's look at that, right? The pole that the sine's hanging down from, right, is attached to a hinge. All right. On one end, we have our rope that has a force, tensional force of 228 newtons. We know the pole is being pulled down with a force of 350 newtons. So we got to figure out what is the y component of the hinge itself. Obviously, we don't really need to consider the x components just because we know it's not going to be rotating or moving in the x direction at all. So let's look at some of our y forces. Okay, some of our y forces, right? We have our hinge, Fy, plus our tensional force minus Fg is going to be equal to 0, right? Because it's going to be the hinge and the rope that are holding up the sine. Putting this all together, right? Obviously, I'm going to put my bigger force first. Plug in my numbers. All right, and this is where we get 122 newtons, which is kind of that remainder. So the hinge itself is providing a y force of 122 newtons, right? And that combined, the tensional force of the rope is what is able to hold up this 350 Newton sine. Okay, another seesaw question. So getting a little more in depth with this one. So we have two students. In this case, they're sitting on opposite sides of an 800 Newton teeter-totter. So kind of key thing, right? This is not a seesaw that has negligible mass. Student 1 is sitting on one side. And they have a mass of 65 kilograms. Student 2 has a mass of 90. So let's figure out a couple things, right? We know that FG is equal to MG. Straight off the bat, we know that student 1 is 65 kilograms, student 2 is 90. So we can go ahead and just figure out their gravitational force, right? We got 637 for our first kid. Second kid, significantly heavier, 82, right? Now, what we can kind of consider is that if you put both these kids on complete opposite ends of your seesaw, obviously the seesaw is going to rotate, right? Because a heavier kid is going to lift the lighter kid. But in this case, the question is asking us to set the kids, specifically the second kid, to be in a position where he's going to balance out the lighter kid, meaning he should not sit at the very end of the seesaw. All right, so let's put it this way. We know that the first kid, the kid on the left, is going to be rotating the seesaw in the counterclockwise direction, and M2, the second kid, is going to be rotating it in the clockwise direction. Our goal is to get it to be in equilibrium, right? So that their torques will equal out. So I'm going to actually, it's going to be kid 2, right? So we're talking about torque, right? Remember, is force times distance. The force of each of these kids is provided by their gravitational force. So FG2, R2, right? That's going to be the torque of the kid on the right. And this is going to be equal to FG1, R1. All right. Now my goal here is to figure out how far from the pivot do I want my second kid to be in order to balance all of this out. All right, so R1 is equal to, let's see. Yeah, because he is clockwise. All right, no, I got this mixed up. Sorry. Right the first time. So I'll just try to remember who's rotating it which way, right? Clockwise kid is going to be M2, right? Yep. M1. Oh, so I do have this right. Okay, never mind. Sorry. Okay, so R2. All right, try and figure out the distance I want him to be. All right, so this is going to be equal to F1 over. Okay, now I know the gravitational mass of my first kid is 637. Key thing I can infer from my problem. Right, it says that student 1 has a mass 65, sits at the very end of the teeter-totter. All right, so if I'm thinking very end, all right, that's going to be a distance of 1.3 meters. All right, this is all going to be over 882. Let's plug that all in, and we get about 0.94 meters. We should add up, right? I know that my heavier kid should be closer to the pivot point, right? So they're going to have less torque. we know they're going to have more torque as they sit further and further from the pivot point. Okay, last little example question here. We have a 3,500 kilogram truck parked on a bridge. If the bridge deck itself has a mass of 6,500 kilograms, find the supporting force provided by each of the two support posts. All right, so this is a good one because, again, this is very like engineering related. So again, in this case, right, we have a bridge. We definitely want it to be in rotational equilibrium. We want it to be in every type of equilibrium. Otherwise, your bridge is moving. And that's only useful if it's like a drawbridge and it's designed to do that. But in this case, right, we're not assuming that. So a couple things here. Just like with anything else, we can establish we want our torque to be in rotational equilibrium. So clockwise, counterclockwise should all be equal out. Now, let's establish a few things. We know with our truck, we're going to define this as FG1. We know for our bridge itself, right, notice I'm drawing my force arrows from about what the center of mass should be. This is going to be FG2. Notice I have two pillars on both sides of my bridge or support posts. So each of those is providing a normal force. So I'm going to call this normal force 1, normal force 2. Okay. Couple other things I can break down. Okay, so this distance, all right, distance from the center of mass of my truck, I'm going to say is D1. Okay, distance to the center of the bridge, I'm going to say is D2, which is 7.5 meters. All right, that's a lot. So let's go ahead and put this all together. All right, so I have my force that's pulling everything in the clockwise direction. Also, I'm going to say that this is D3, right, the entire distance. All right, so we'll say clockwise. So I have my normal force 1, so the left pillar, and the force, right, distance from its pivot is going to be 15, right? So this is, sorry, I'm using D instead of R. Doesn't matter, same thing. So D3, right? And this is going to be equal to FG1 D1 plus FG2 D2. All right, so notice, right, there's two things being held up, both the bridge itself and the truck, right? And the main thing that's holding them up, right, on this end is going to be the torque from the normal force of the left pillar. Now I'm going to do, well, yeah, I'm just going to start with this. All right, so I'm going to solve for what's the normal force for the first pillar. All right, so I'm just solving for normal force 1, FG1 D1 plus FG2 D2 all over D3, get about 34,300 plus times 5 plus 63,700. Again, these are D2 all over 15. So I'm going to get about 43,300 newtons for my first net force. All right. So that's a lot. But we're not done. All right. Because then I need to also figure out what's the normal force of the second supporting pillar. So let's put it all together. Do this in a different color. Because it's not just one pillar holding it all up by itself. All right, we're mostly talking about forces in the y direction. So the net force in the y direction is the normal force of the left, right, which we established, plus the normal force of the right minus the two gravitational forces. And because this rotational equilibrium, right, the net force in the y direction is going to be 0. Okay, so we end up with solving for normal force of the right pillar. We get Fg1 plus Fg2 minus Fn1. Here, just plug in the numbers I know. Okay, taking my two gravitational forces for the truck and the bridge, and subtracting the normal force of the left pillar, which we already calculated. Okay, so Fn2 is going to be equal to 5,4,700 newtons. All right, notice they're not the same. The main reason why is because the truck is closer to the right pillar, so there's more normal force because there's more gravitational force on that particular side. All right. That's also why, right, when bridges collapse, they're going to collapse on the side that has more mass being applied, typically. All right. And not the side where the mass isn't. Right? Just should match up. When there's no truck on the bridge, then those two normal forces generally should be equal. Right? And that is the end of this second lesson. We'll get into torque not at 90 degrees in the next one.